Hello, this is Aaron, and I just wanted to do an update about day lengths because I've made some progress in how to calculate the day lengths from my model so that I can test those day lengths against reality and against other models. Um, so you might remember, if you've watched my videos before about day lengths, I put together a graph that shows day lengths by latitude at various days. But the way that I built that graph was actually literally put points down, and I would watch I'd run my model and watch when this night and day ticked over the dot to calculate, and then you can watch actually calculating how long the nights and days are up here. But that method was fine just initially to get an idea of whether it made any sense at all. But what I wanted to do was come back and actually calculate the day lengths as a function. So what I wanted to do is to get to develop a function, calculate what the function is that tells me, given any latitude and given a particular time, day in the year or time in the year, what length of day would we expect? So you'd be able to pass these two things in and get out a day length in terms of number of hours. So that's what I was looking to do. So that's what I think I've managed to do now. And I want to just show you how I did that and what the results are. And it looks very cool actually. So first of all, I just want to show you that, say I'm standing here in Africa. So I put a dot here, so we're in North Africa. So this is when night falls, okay? So I'm at the sunset, I'm on the sunset line. I just want you to look at the fact that the sun and moon here are on this line here. Okay, they're on a line across here. It's not perfectly horizontal, it just happens to be nearly horizontal, but according to where I put my dot. Okay. Now, this is the point where night begins. The point where day begins is when this comes right around and hits me. So let's just wind it forwards to where day begins. So if you watch it go round, and you'll note that this is I've chosen basically the middle of the winter so that we have a big distortion effect. Okay, so here I've stopped it. So we've just had a night and we've just hit dawn. It could have been the other way around. It could have been, the start of the day to the end of the day. It's the same geometry. But what I want to show you is that this line here, you see this line, the sun and moon, is not where it was before. So it was nearly horizontal before. Now it's up here. And if we wind it forwards again, and let it go again, get to a night, get back to night. There we go, it's back to where it was before, pretty much. Not exactly actually, but pretty much where it was before. And then we wind it forwards again. There we go, so there we've got them on this line again. So we've got these two lines, one for the dawn and one for the dusk, and you can imagine these two lines, and there's an angle between them. Now, what you can do is, if you can calculate the angle between those lines, that tells you how long the day was or the night was, because the sun and moon revolve around 360 degrees in 24 hours. Okay, so in one day or night, these will revolve around. So what you're looking at is the angle between those lines is the angle the angular difference between 180 degrees and the distance the sun or moon have to travel to get to the night or day. So let me try and explain that more clearly. The sun is here when we have sunrise, okay, and the moon is over here. When it gets to sunset, you'll see that the sun did not go a full 180 degrees. It went 180 degrees less, this angle between the two lines that we saw. Okay, and then here it will have to go we'll have to go 180 in addition to that angle to get around to the day again. So that's why the day and night are not the same length. One of them is shorter than the other, and we can calculate the length of the day or the night if we can calculate that angle, because we know the time it takes for the sun-moon system to go through that angle. We can calculate that exactly. So what I've done is to do that calculation. So I'll just show you how. It's basically a trig problem which can be broken down into triangles. So let me just get this open. So I did a little hand-drawn crappy diagram. But I just want to give you an idea of what's going on. So this line here, right, is where we have the sun at dawn. Okay, so the sun is over here at dawn. Okay, and the North Pole is here. And somewhere here, there's the midpoint. Okay, I'll just try and move it so you can see. So there's the red midpoint. Okay, and the North Pole's here, and the sun was over here. So we have this line here. Okay, and on that line, so we're going to call the distance from the North Pole to the midpoint. I'm going to call that distance in this diagram K. Okay, and then we've got another length, which is the distance between the midpoint and the sun or the moon at any time. So the sun and moon in my model are always the same distance apart, and that distance is 2 times L. I'm calling it L. So L is the distance from here to the midpoint, the distance from the sun to the midpoint, and the distance from here, the moon to the sun, is always 2L in my system. So I'm calling that distance L, okay? And the distance I said before was K, and the distance K is from the red midpoint to the North Pole. So one distance in the diagram is K, this small distance here, which varies from 0 up to 24 degrees in my model, depending on the time of year. So K is something that varies according to time, okay? Whereas L is just this fixed distance, okay? And there's me down there. So in this diagram, we've got the North Pole, we've got the sun at dawn, and there's me, okay? And we know that the distance from me to the sun at dawn is L, because this dawn goes in a is a semicircle. In the yin-yang shape, it's a semicircle, radius L. Okay, so the distance from me to the sun is L at dawn. So that's why I put L on this length here. On this length here, from the North Pole to the sun at dawn, so from the North Pole to the sun is this distance K to the red dot plus this distance L to the sun. So in the diagram, I've labelled this length here as L plus K, which is that distance from the North Pole to the sun. So we've got this L, we've got that L plus K, and this distance, which is the third side of the triangle, is given by the latitude, because that's me, it's the North Pole, my latitude is that distance, okay? Well, I'm using a latitude where I just to keep it simple, I start at 0 and just go up to 180. You can 0 latitude at 90, but I'm just using latitude as a distance. Angular distance you could call it, but it's the same as a planar distance in the flat Earth model. Anyway, so it's 90. So the distance from here to the equator, for example, would be 90. Distance from here to me is this latitude length here. So you can make this triangle, and because we know all 3 sides of the triangle, we can calculate this angle beta. Okay, so that's one triangle. The second triangle I've drawn on is when is after it's been rotated round. So you've gone from the dawn to the dusk. So at dusk, the distance from me to the moon is now L. Okay? So you get this other triangle here, but this is the moon at dusk, and that was the sun at dawn. The distance from the North Pole to the moon at dusk North Pole to the Moon is given by L, which is this distance from the Moon to the red dot, minus K, the distance from the North Pole to the dot. Okay? So in this triangle, instead of L plus K to the Sun, we've got L minus K to the Moon. Okay, so it's this interplay between these things that creates the behaviour we'll see. So we've got L minus K, L plus K, we've got L here, we've got the latitude here, and we know that the distance from me to the Moon is also L. So now we've got two triangles, we know all the lengths of all the sides, and we know that in order to calculate this angle, which is the one we want, okay, the angle between the Moon at dusk and the Sun at dawn, okay, that distance can be calculated because if we can calculate this angle and we can calculate B, then we can subtract them to give us this angle. So this angle is given by these three sides of the triangle, and this angle B, which I already showed you, is given by these three sides of the triangle. So you can basically then just plug them into some trig function, and then you can then calculate that what you have then is this alpha, this angle in terms of K. So we want alpha in terms of latitude and K. So we've got this in terms of latitude and K. Now K is a function of time. K is the distance from the North Pole to that red dot. At the solstices, that's 0. So K at the solstices, the red dot is on the North Pole. The Sun and Moon are both on the equator, so K is 0. So if you imagine what this looks like, if K was 0, these triangles become the same. These triangles merge. The angle here drops to 0, if you can imagine that. Anyway, you can look at that later and think about that. But that's why at the solstices, when the red dot is in the middle, everyone's going to get the same night and day lengths, and the night and day lengths are going to be the same because these triangles become the same and the angle falls off to 0. Now this angle alpha, I want to remind you why it is we're looking for this angle alpha. It's because the Sun is going to go around imagine the Sun going round, it's going to go around 180 degrees less this angle alpha, okay, when you hit night. So from dawn to dusk, the Sun is going 180 degrees less this angle alpha, and the Moon is also obviously going the same angle. So the angle that the Sun has travelled through is 180 less this angle, and that angle, we know how long it takes the Sun to travel that distance, that angle, because it travels 360 degrees in 24 hours, which means we can calculate from this angle, we can just calculate directly from that how many hours it takes to get from dawn to dusk. So then we have the day length. Okay, so we have the day length as a function of latitude and date. So what I did is I wrote a program to implement this, okay, and this program, which will just run, produces a CSV file. So what it's going to do, the program is basically just going to produce, so I ran the wrong one actually. The program is just going to produce, here we are, a list of day lengths. So what it's going to do is it's going to go through all the latitudes, like 2 degrees at a time, and it's going to go through all the days of the year, and it's going to calculate using this function what I think the day length should be. So I then can open this up in Excel, but it's not very useful to look at here. What I can do is take this